get underway. So welcome everyone. You're at the part 2 of the March edition of the Data Engineering Meetup. So we already had our first 2 talks today at midday during the regular time slot. And we've got Katz, the co-founder and CTO of Treeverse, the company behind lakeFS. He's joined us all the way from Tel Aviv. And so for him to talk at midday, it probably would have been about 3 a.m. in the morning. So we didn't want to be that mean to him and make him wake up that early. I think that would have been a bit tricky. So we've just used the magic of the interwebs and sort of made a good time zone for him to come and present. It's actually 9 a.m. for him over there. So I think it probably works out just right. Although I have been warned he is pre-coffee. So I'd struggle actually getting a presentation out of myself pre-coffee, but good luck. So lakeFS, obviously Oz will take us through absolutely everything about it, but it's a little bit like a Git-like repository for your data lake. So I think it's a lot of us are looking at data lakes and the like, but data versioning is I guess quite topical in many respects. So I think that'll be really interesting to see what insights Oz has to share with us and to take us generally through lakeFS. So without further ado, take it away, Oz.
Okay, hi, thanks Peter for introducing me, and thanks for hosting and for this awesome community. So yeah, it's 9 a.m. here, 6 p.m. your time, so that's going to be interesting, at least for me. So let me just get started sharing my slides for a second. All right, you should be able to see them now, hopefully. Cool. Okay, so before I dive into lakeFS, just a couple of words about me and who I am. So my name is Oz. I'm the co-founder and CTO at Treeverse. We're the commercial entity or the company behind lakeFS, which is an open source platform, which we'll discuss. My background is mostly around data engineering. So like companies that work at a certain scale, doing analytics or data processing. These were kind of my bread and butter for the past 15 years or so. Before starting Treeverse, before starting working on lakeFS, I was VP R&D at a company called SimilarWeb, which is an Israeli analytics company. It's a pretty big one actually. Where we managed data lake spanning several petabytes, so a pretty sizable one. And we probably suffered from every possible downside of managing a data lake at scale, which is pretty much a big contributor for the reason why we started lakeFS to begin with. At SimilarWeb, I also I had the honor of accidentally deleting about 1 petabyte of data, which I'll discuss more in depth later. So the scars are on my back. And actually, if you stay tuned to the presentation, I'll also discuss how lakeFS could have prevented me from doing that. It wouldn't have prevented other stupid things I've done through my career, but this specific thing could have been prevented. So yeah, so let's talk about what lakeFS is. So I'm going to talk about the product itself, what it does, how it's being used, and then go over a couple of like main use cases for it, like main reasons why people should be using lakeFS. At the end, I'll try to kind of dig a little deeper into the architecture, so like how lakeFS is built, how it scales to petabytes of data, like a little bit behind like the data model for it. And hopefully like questions through YouTube from the live stream or from Zoom or from anywhere else where they might come. I'd be happy to answer those. All right, so let's start with what lakeFS is. So lakeFS, if I had to give like the one sentence, it's an atomic version data lake on top of object storage. That's kind of a lot of words put into like one sentence. Basically, what it means is that like a lot of companies now are using an object store to host their data lake, stuff like Amazon's S3, probably the most popular one. But historically also HDFS or other distributed file systems were used for this. And of course, the other cloud providers have their own versions of an object store on GCP and on Azure. So what lakeFS is basically a layer on top of that object store. So like it's not a storage engine or an object store in its own, but it's kind of like a wrapper around an existing one. And what it does, it adds capabilities that we believe are missing from an object store for it to be a good data lake. And those capabilities mostly revolve around versioning. And I'll explain why in a second. But the idea is to provide something that sits between the object store itself, like wrapping it, and whatever tools already exist in the organization. Like the whole premise of a data lake is that I have this one place, one centralized repository inside my organization, where all data sources can write to, and all query engines and processing engines can like read from and do queries on. And like everyone speaks the same language, right? If I can write files to S3 and I can read those files, I have systems that are now being integrated. I can spill Parquet files from like my Kafka topic and then read them in Spark or read them in a Presto query. And it all works because the lowest common denominator is just flat files on S3. And it's a great architecture and it allows everyone to kind of bring their own tools and like allows you to experiment easily with all kinds of different technologies. But at the end of the day, it also creates quite a few problems because now we have this huge central repository, which is basically like a data lake is a nice name for a shared folder, right? It's all like one big place with all kinds of different paths where files are stored. And that gets really tricky and hard to manage. So like if I try to deconstruct lakeFS into what it actually does, so as I mentioned, it's a wrapper around the object store. So like underlying storage, we support all the major cloud providers. So like Google Cloud Storage and Azure Blob Store, and of course, Amazon's S3. And we expose an API, which is a superset of the Amazon S3 API. So if you have an application that knows how to communicate with S3, it can also communicate with lakeFS. So it's kind of transparent for the application. If I have a Spark job that reads and writes from S3, all I have to do is change the endpoint from S3 to my lakeFS installation and keep on working normally. lakeFS does all the magic like in between. So we're API compatible with S3, but we add to this API like what we believe are the missing capabilities, and that's the versioning aspect. So everything that happens within my S3 now basically behaves like one giant Git repository. So I can create branches, I can do commits, I can diff between commits, I can merge them, I can roll back a commit, I can go back in history, like all the like powerful primitives that Git provides, I can now use on top of a data lake. And of course, like code and data are very different, especially when it comes to scale. So the idea is to take like the user experience or the feeling of having Git, but having it scale to multiple petabytes of data, potentially billions of objects, with it being as transparent as possible, like for my critical path. So like my Spark jobs, my data streams, everything should still behave normally as it did before, except for right now I have those new capabilities that were added. So what does change? So when you communicate with Git, you usually do it in the context of a branch, right? So I want to operate on a specific branch. So if up until now I would just communicate directly with my files by like doing the bucket name / the path to whatever collection I have, I'll just prefix it with the name of the branch. And if I create a new branch, all I have to do is change this prefix, and now this new branch like still shows the entire data set, like the entire like few petabytes that I have or billions of objects that I have, but it's isolated within its own branch. And we'll talk about why that's good in a second. But like the idea is that like my existing code and my existing applications, it's kind of transparent for them. As long as I can add a prefix to the path that I'm reading or writing, I am now suddenly branch aware. And now this also extends to like the Hive Metastore that many people are using to kind of decouple the storage and the schema. So if I have a table that was linked to a set of files that were hosted on a certain branch, I can easily create a clone of it for another branch that I'm using and work on that branch also on the Hive side of things. But the idea is that it should integrate as seamlessly as possible into whatever existing workflows that I have. Okay, so why does it exist? Why do we think that Git for data is a good idea? Well, first of all, because versioning is a good idea, right? So if I think about the way that we manage code bases, Git provides very strong language to do it. And if you think about Git from a data store perspective, which is kind of an interesting mental exercise, you find that Git has a lot of properties to be a good database. Actually, it's a terrible database in some aspects because managing code files is very different from managing tables. But the primitives that it exposes are pretty powerful. So, for example, Git, for everything that I do, for every change that I do, Git is going to create an immutable version, like a point in time that I can always go back to. So if I did a change and I'm unhappy with it, I can simply revert a specific commit and go back to the way things were before it was introduced. If you think about data systems or a data lake where everything is kind of like a big shared folder, this is a pretty powerful primitive, right? So if I did a change, if I have overwritten some data or deleted some data, being able to just revert that operation atomically and safely is a pretty powerful thing. Additionally, by having Git branches, I now get isolation. So kind of like transactions in maybe a relational database. Once I create a branch, I have my master branch, which is kind of like my production version, and then I can create a branch from master and call it my terrible branch. That's the name. And I can do whatever damage I want within that branch, right? I can delete files, I can mess around with whatever is in there. I can experiment with new technologies. I can do pretty much whatever I want on that branch. And I know that my master branch is not affected, which is also a pretty powerful thing. If I think about back to prior to lakeFS, working on data on a data lake, people were really thirsty for this ability. And I want that isolation because first, I don't want people to change the data that I'm working on underneath my feet. I don't want it to move as I'm working on it because if I'm experimenting with something, that's going to interfere. And on the other hand, I don't want to mess anything up for someone else. So the first thing I would do is, okay, let's take this data. I'll copy it to some other path because I don't want others to mess around with the data. And then once the experiment is done, either I remember to delete it or maybe the usual case where I don't. And then I just have all kinds of copies lying around, which is also pretty terrible, right? From a compliance or security standpoint, being GDPR compliant means I have to remove all kinds of data from places. And if I don't know those places, that's kind of a problem. And of course, Amazon really likes that ability because I create a lot of copies. I end up paying for my S3 bill is going to jump pretty quickly. So being able to create a new branch where no data is actually being copied, that's the Git model. I create a new branch, it points to whatever existed on my previous branch, and from here on out, it's going to copy and write. Right? So every change I do is on top of that immutable version that I branched from. So that's a really powerful thing. Additionally, it means that if for every change that I'm introducing to my data lake, even production changes, I'm doing it inside its own branch. I'm doing a commit and then merging it back, kind of the same workflow you would do for code. It means that if anything broke at any given point in time, I can easily go back to the exact commit that introduced that change, see exactly what happened, and if there was a bug, I can easily reproduce it. Right? So I see that, okay, this point in time, I introduced some data that ended up being corrupted because of a bug in my code. So I can go back exactly to that commit, test my changes in isolation, see that my changes actually fix the problem. And then once I'm actually certain that it fixes the problem, I can introduce the changed data or the updated data back into production atomically, which is also something that's really, really hard to do today because we don't really have a good separation between readers and writers on a data lake, and branches provide that ability. And this is something that like we see at a lot of companies where they kind of try to fix this problem using some kind of like external hack, where maybe I have my own job running, and then when it's finished, the last thing in my Airflow DAG would be to update some other key value store, or maybe add some flag to the Hive meta store to say that I'm done. And only once I say that, I expect other people to know that the process actually finished and now they can read this data. But the thing is that it's not like a standardized thing. And if the consumer, on the other hand, is just looking at S3 and sees, oh, okay, cool, I have new data, they're not aware that it's actually still being written or it hasn't been tested yet. So like the whole concept of separating readers and writers is something that's like, it's painful that it's missing. For databases, this is trivial because we have transactions. So until I do like a commit, no one else would see the changes introduced in that transaction. But if I talk about data lakes, where I want to maybe change like a few different tables at a time, regardless of what format I'm using, this separation doesn't really exist. And branches reintroduced that concept. The other nice notion is that merging a branch, so I can do whatever changes I want on my branch. Eventually, I'll want to introduce them to my main branch, to my master branch. Doing that in Git or also in lakeFS, as we'll see later, it's an atomic operation. So you're creating a new commit, and then you're just saying, I want to point master from the previous commit to the new one, which is atomic. So as far as anyone else who's observing the data lake on its main branch, either I see all the new changes that were applied, or I see none of them, but I'm never going to see any like intermediate state or anything that will maybe have failed in the meantime. Which is also kind of liberating, because as a consumer, I don't want to care about like what might be in the middle of production or maybe isn't really safe to read. If I see data, I want to assume that it's fine and read it. The last part is, okay, maybe I've done all those crazy changes and maybe I don't want to introduce them. Being able to just discard changes and say, okay, this was just some experiment, I want to roll it back, becomes trivial. And if I talked earlier about me deleting like about a petabyte of data, this would be like a killer feature for me. So the way I deleted a petabyte of data was that like we had a pretty complex retention logic. And there was like this one specific Spark job that everyone simply hated, which was aptly called retention. And what it did is that it applied all kinds of business rules to understand which data I can now safely delete. Like data was very interconnected, like I had all kinds of tables with different partitions for different dates. And under certain rules, I could delete like from one table, but that meant that I also had to delete like correlated data in other tables. So it was kind of a pretty complex job. So it's not something that could be easily solved using like lifecycle management offered by S3. So we had our own logic, and everyone always hated that job because testing it is kind of impossible, right? So even if I went through the length of creating like a staging data lake where I have maybe a sample of my data, it's never going to be exactly the same as my production data. So I'm never going to be confident about whatever change I'm going to introduce to that job. And because this job deletes data, like there was no logical separation between the act of deleting the file and having it like disappear from my storage, right? It kind of makes sense. But Git enables exactly that. So if I had something like lakeFS, I could create a branch, run that job on exactly my production data, see a diff of, okay, these are the objects that are actually going to be deleted. And then only once I validated this branch and even maybe let some other jobs run on it, I could say, okay, this change looks good, I can now merge it. And then this whole kind of a close your eyes and pray approach to doing data engineering, I could do something that's a little bit better. So like in a perfect world, I'd have Git to solve all those problems. Of course, Git doesn't scale to data lake size, but lakeFS does. So basically everything that we talked about, I can easily do with lakeFS. And it provides a language that, as you can see, is very similar to the one that I already know from Git, right? So like, we believe that like it shouldn't be surprising. Like if I'm using Git already, if I'm familiar with Git, which I'm assuming most of you are, using lakeFS should be like as intuitive as what I'm already using, as what I already know. So most of the commands are kind of similar to a degree, or they at least look very much like the ones that I would do using Git. But this whole thing happens on a data lake, wrapping S3 or whatever other object store I'm using, and exposes an API which is also compatible with S3. So I can create a branch, and then using this new created branch, I can pass it to a Spark job to read. And I know that this Spark job now runs in isolation. All the changes that happen within that Spark job that it introduces happen on this specific branch and not on my master branch. I can see then a diff of what my Spark job introduced, and then I can decide if I want to merge it or not. Like I get the exactly the Git experience, just on data lake scale, data lake size. And this is something that we believe is really powerful. So we talked maybe a little bit about like the technical aspects, like the primitives that Git introduces, or like the new language that lakeFS enables. But I want to discuss more like why it's actually something that could really be useful for like actual real use cases for stuff that people do with data. So the first use case would be a development environment, and this is something that like historically, like every organization that we see, it's always a struggle. Like it's always kind of a double-edged sword, kind of. Either I test everything on production, which surprisingly, or maybe not surprisingly, that's what most people end up doing. Because creating like another like parallel universe or another data lake is really expensive and really hard to maintain. Or they try to go through the length of creating like another staging repository, but then it's either not updated frequently enough, or it creates, or maybe I write only sample data because the cost would be too high. So it's like an environment that like I pay all the cost of having it around, but I don't trust it enough to actually test my code or my changes. And this is because it's always going to be either lagging or too small behind what production is for it to be reliable. So the concept of like using something like Git, which offers us like all those isolation guarantees, but I know that whatever data I'm pointing at is the actual real production data, and with the same scale that production has, and with the same exact characteristics of data that production has, is a very powerful guarantee. So by having a development environment that's based on lakeFS, I know that whatever I'm testing, it's going to work exactly the same as it would when I pass that code to production. So what does this enable us? So first of all, I can do experiments like very easily. So I don't need to copy any data around anymore, because once I create my own branch, I know that it's frozen in time until I decide that I want to update it. And I'll do that by merging the master branch back into my branch. So no one else is going to be touching my data. And on the other hand, I know that whatever change I'm doing is not going to influence the production view or the main branch, because I haven't decided to merge it yet. So this allows me to create multiple branches. Branches are very cheap in lakeFS. A branch for each like version of the experiment I'm doing. Maybe I'm tuning a parameter on each one. Maybe I'm trying a new algorithm, or whatever change I want to introduce. Maybe even like changing some of my infrastructure. Maybe testing a new version of Spark or something like that. I can do those changes in isolation. And then because of the way lakeFS works, all branches are available at any given point in time. Like I don't have to clone them or copy them or anything like that. I can simply change the prefix of my S3 endpoint, and then I'm addressing this other branch. So I can make changes. I do them in isolation, one branch per experiment. And then simply by creating those branches, I can then read it using a Spark job. I can create a data frame for every branch or for every change that I introduced. And then compare the results, have them live in parallel for a while, maybe test other jobs and see how they are affected by those changes. And all this, of course, happens in isolation. And like this is maybe one of the biggest changes from Git, where in Git, where I have to like check out a specific branch, and then like I have one version living at a time inside my own like cloned repository. In lakeFS, I can address whatever branch I want at any given point in time, because it all lives remotely anyway. So this will be an example of how I would create like maybe 2 experiments running in parallel, and then using Spark to do some aggregation to compare the results of those two branches, of the changes introduced by those two branches. Same thing would work for any other framework. So this is an example with Presto, basically doing the same thing, only here I'm creating an external table that points to an external location, which is actually mapped to a lakeFS branch. So we can see example /main, main being the branch name, and then the path to wherever this collection leaves. And from here, I can just use SQL on top of Presto to query the data within that branch. So the second thing, so once we have like a development environment, I can do those experiments in isolation. I can introduce new codes safely. But what happens when I want to introduce new data? So we talked about a data lake being kind of like a giant shared folder. And like I want people to be able to write new data and to introduce new data sources, introduce changes into this data lake. But at the same time, I also want to kind of guarantee some like rules that everyone has to play by, maybe a set of best practices. Like common ones would be don't introduce breaking schema changes to production tables. That's kind of a basic one. Or maybe if you want to have something on the production data lake, it has to be like in a columnar format and not like CSV files. Or maybe you want to do some metadata validation. So maybe you're using something like Marquez or Munson or anything else to like register the metadata behind every table or every logical collection. And you want to ensure that every data that gets written to my data lake is also registered to that metadata repository. And if you think about it, it's the same like level of verification that we would want for code. So like we would see this as kind of like doing CI, but for data. So how does this work? So again, it's pretty similar to the way we do it nowadays with like Git or GitHub, right? So I'm working on my own branch. Like I don't want to work directly on master or on my main branch. And then like if I want other people to be able to see the changes that I'm introducing, I do this by merging into master. And lakeFS has a notion of what we call pre-commit and pre-merge hooks, where I can define a set of like logic, a set of actions that should happen and that should pass when you're trying to commit something or when you're trying to merge something. And like the most common use case for this would be, let's set some ground rules for what could be merged into the main branch. So in this example, maybe I'm doing some change and I'm introducing a few Parquet files, which as far as I'm concerned, that's fine, that's a good change. But I also added like a CSV file there. And that's of course a trivial example. But the idea here is that I can prevent this change from ever reaching my production branches by using those hooks. So I can define a hook that says CSV files not allowed. It's going to run for every merge operation that happens into the main branch. And it's going to stop a merge from happening if it doesn't pass this validation step. So this sounds kind of trivial and kind of simple. But if you think about it from like the data consumer side, it's actually a very powerful guarantee. Right, so I can be assured that if I'm reading from the main branch, I'm always going to see only this set of specific formats, or maybe only like this specific schemas that are allowed, or whatever other like business logic that I can think about. And I have this guarantee that it's always going to be that way. Of course, like more contrived example would be ensuring that every partition being written is either completely replaced or fully written. So I want to guarantee that data is immutable and that it doesn't change retroactively. So using these tools, I can now do this very safely. So this is a bit of a longer example. I'm actually showing the code of what this pre-merge hook would look like. So in this example, I'm using PyArrow. PyArrow is a nice Python library that basically integrates into the Arrow ecosystem. And I'm using it here for something that's pretty trivial. I'm using it to read the Parquet file and to check its schema, see what columns it contains. And on this example, because it's a pre-merge hook, I'll start by doing a diff, like show me what changes are being introduced. I'm looking for Parquet files, and for each Parquet file that's being introduced, I'm going to like read its metadata, see what columns it contains. And if it contains a user ID column, I'm going to raise a validation error. Meaning, I don't want to see a column with the name user ID within this collection. It's not allowed. Why? Because it's personally identifiable, and the prefix I'm working on is maybe /public or something like that. And this type of column name is not allowed there. And now I have this guarantee that anything written to public /something will never contain this user ID column. So like with 5 lines of Python, I can now create like a policy for my data lake that otherwise it would be pretty hard to maintain. And I know that anything that happens on the main branch will always go through this validation. So what I can use it for, I can do schema validations, I can do format validation, I can look for backwards incompatible changes that might have been introduced. I can look at the metadata that the table has to be like registered for, or I can do my own business logic. Like I can define whatever behavior I want that happens before something gets merged into production. Like if you think about it, like comparing to code, anything from linting to actually testing the data, I can do anything there. And this is very useful when I'm trying to introduce new types of data, or maybe a new collection, or changes to existing tables. This is very powerful for that. On the other hand of that spectrum is what we call continuous deployment for data. So like, for the most part, I'm not introducing new tables, I'm just writing new data to existing ones. And this is something that's usually like an automated process. Maybe I have an Airflow DAG, or I have a streaming job that's happening and keeps on writing new data to my data lake. It's probably not going to change the schema. It's not going to create new tables. It is going to create maybe new partitions or add to existing tables with new data, more recent data. And here the set of like concerns that I have is a bit different. And here it's mostly around the data quality. So what happens if like I rely on some other data source upstream? Maybe it's like an SDK that's running inside my web application, or maybe it's just another collection that I keep on reading from, doing some processing on, and then writing. Those upstreams can also change and maybe introduce a bug or an issue. Or maybe I just changed the code of like the logic that I'm using to process this data, and now I'm introducing something that could be problematic for the data downstream. So like the notion of continuous data deployment, or CD for data as we call it, is being able to continuously check for data quality issues before data actually reaches production. This is kind of a key aspect of this. So nowadays there are like great tools to do like data quality checks, stuff like Great Expectations or Monte Carlo, or like many other frameworks that do this. And they look like at the statistical properties of the data and try to compare it like with the historical one, or maybe ensure that it meets a certain set of constraints that I've like configured. But those tests can only run once the data has already been written. And by the time it has already been written, it may have already been read by someone else. So if I do find an issue or a bug, someone else's like Airflow DAG has already started, and they've already written some data based on my wrong data. And now it's like this entire like graph of dependencies that is now starting to like bubble and propagate because of a change I introduced that was bad. So continuous deployment means basically merging into my master branch at like given intervals, maybe every time my Airflow DAG finishes running, or maybe like every few minutes or every minute if I'm reading from like something like a stream or Kafka. And every time before I do this merge into my master branch, I want to run some validation on the data itself. It could be something simple, like maybe just aggregate everything, do a count, and see that like the number of rows that I'm getting is within like a range that would make sense. Maybe 50% up, 50% down from what I had a week ago, but no more than that, something like that. Of course, real life examples would be more complex than that. But I can run those hooks, and I can have this like validation happen before data actually ever reaches my main branch. And if something does go bad, now I have this commit, this point in time that I can refer to, and I can say, okay, this is the change that introduced this problem. I can now safely examine the data at this specific point in time, because this commit is immutable. I can fix the problem. I can look at what's causing it, maybe introduce a workaround or a fix. And only once I have that fix in place, I can like try to run through this validation again. And if it passes, then I'm back to normal. And I can do this before it actually ever reaches anyone else, which is kind of like the powerful thing. So in this example, for every commit that I'm doing, like this is an example where I'm reading from Kinesis or Kafka or any other stream. And that periodically, maybe every 1 minute, I'm doing a commit and then merging it into my main branch. And every time I'm doing this commit, I'm not only recording like the metadata for like the commit itself that was introduced, but I'm also writing like the offset of the topic I'm reading from, and also maybe recording the git commit of the actual data consumer that's reading from the topic and writing to my object store. And I'm adding this metadata to my lakeFS commit. So if something fails and I now see that, okay, this hook doesn't pass validation anymore, it will point me exactly at that commit where I can see like exactly the offset that I've read so far. And once I fix the problem, I can just simply continue from that offset, meaning I can rewind like my history both on lakeFS and on Kafka, and they're coordinated with one another because they expose this thing, this notion of an offset. So like how would I hook up a data stream into lakeFS? So basically it's pretty trivial because Kafka Connect and most other frameworks know how to speak with S3. All I have to do is change that store URL. Instead of pointing at S3 directly, it's going to point in my lakeFS installation. And from there, I get versioning for free. So these were like the major use cases. So it's basically like trying to recap it. It's being able to create a development environment that's safe to work on, and it actually represents my actual production data. Being able to do continuous integration, as we call it, or like safely introducing new types of data or changes to the data, and then continuous delivery of data, meaning I want my recurring jobs and like my ongoing workflow to be safer by introducing data quality checks. These are the main use cases for lakeFS. Of course, there are all kinds of other creative uses. One that I haven't even mentioned, but lakeFS makes very trivial. Even if I didn't do all those nice steps and I ended up introducing a breaking change to production, or maybe I've done something terrible in production, using lakeFS, I can always say, okay, take my master branch 2 commits back in time. Like this change was bad, I introduced it by mistake. Just being able to simply revert an operation and do it atomically and like not having to jump through all the many hoops that I would have to go through nowadays is something that's like very liberating. We made the cost of mistake much cheaper, meaning we can take more risks, we can innovate more, we can experiment with new types of data and algorithms, and it's now much easier. So I don't have much more time, I think. So I want to do maybe like a very brief overview of the architecture of lakeFS. And after that, of course, we'll be happy to answer your questions. So of course, lakeFS is not Git. The scale factor is very different. Like we're talking about potentially a lot more data. So like not millions of objects or thousands of objects that like my Git repositories will probably contain, but billions of them. The velocity of changes are more frequent. Like if I have automated processes or dogs or stream processes that introduce commits, I'm potentially reaching millions of commits per day. And those changes are usually data objects and not like lines in a file. Like I wouldn't merge 2 Parquet files together. It wouldn't necessarily make sense. So I'm working at the object level, meaning lakeFS is built in a way that's a bit different from the way that Git works. So like it exposes a similar API or a similar set of behaviors, but it works a little differently. So the way it works is that lakeFS exposes what we call the S3 gateway, and this is what my applications communicate with. As far as they're concerned, they're just talking to S3. This S3 gateway speaks to what we call the metadata management layer of lakeFS, which handles all the commits behind the scenes. And these commits, while they kind of look like Git commits, their data model is kind of different. So it's kind of a flat tree for each commit. It's composed of what we call ranges. Each range contains like a consecutive set of ordered key values, basically, where the key is the path in the object store, and the value would be a pointer to a location in my S3 bucket or my whatever object store I'm using. On top of each range like that, I have what we call a meta range, which basically collects a set of ranges together to compose one commit. So it's kind of like a very flat tree. So every time I create a new commit, what I'm doing is that I'm pointing to a new meta range, which points to most of the same ranges that like my previous commits had, except for the one containing my change. So creating a commit is not very expensive. All I have to do is create like this new range file. And what I'm getting is for each commit, I have an entire snapshot of the entire data lake at that specific point in time for that branch. Another nice side effect of that, and this is also kind of resembling the way Git works, is that now creating branches is very, very cheap, because all I'm doing is just creating another pointer to an existing commit. And this kind of satisfies the copy and write properties that we wanted. Of course, it gets much more complex than that in real life. I'm going to share these slides. So I have a document linked below, like explaining in depth the data model and how do we scale this to billions of objects. And with that, I think I will conclude the presentation. So thank you, everyone, and thanks, Peter, for having me. And as I mentioned, would be happy to answer your questions.
Well, thanks once again, Oz. That was a really cool presentation. I think I've got a ton of questions. We've got a couple coming through from the, the YouTube chat. I think you've answered a couple of them. I think Naomi asked some interesting questions around sort of, whether you can do three-way merges on files and stuff like that. And I think you kind of answered that pretty well. So there's so many use cases for lakeFS, like using version data and a bit of a software engineering workflow with data. To be fair, it seems strange that this isn't more prevalent, given that how much stock we put into unit testing and integration testing and software development and data pipeline development, that we don't do the same for our data development. But I guess, like the easiest sort of thing that comes to mind is, I guess, with machine learning, and feature engineering, that you'd use something like this. Where do you see, like, a lot of your customers? You're an open source tool, but where do you see a lot of your customers coming from? Is it that machine learning use case, or is it even, even more before that?
So it's pretty interesting, because so far, like, we haven't like found this one specific place where we say, okay, lakeFS solves this very specific problem, right? If you're doing machine learning, then you need lakeFS, and for everything else, it's nice to have. So like what we see, and this was kind of like our assumption to begin with, is that version control is something that's so low level. It's like it's so much a common denominator that you want to have within your organization, and you want all the use cases to be built on top of that. So like if you think about it, you don't have like Git for Node.js and then something else for Java, right? Everyone's using like the same language, the same tool, because it's such a low level thing. Like I have this one language within my organization. Regardless of what project I'm looking at, I always know that there's probably going to be like a master branch and people are not going to be working directly on it, and then merges are going to happen. Like this whole notion is something that, especially like on a data lake where I have all these different use cases, like from machine learning to analytics to like analysts doing queries. Like I have so many different use cases for it. I want everyone to be able to speak the same language. So like what we're seeing is that, especially where you have all these different use cases, is where lakeFS comes in really handy. Because I know that like my machine learning guys are going to be creating like experiment branches because that's what they care about. And then my data engineers, which are building like production pipelines, they're using the exact same terminology, but they're doing it to like version the data that they're introducing inside their like Airflow jobs. And everyone speaks the same language.
Handle schema evolution and things like that. So this is specifically targeted at, blob stores like, S3 and stuff like that. Are there any plans to extend this into, big RDMSs like, I don't know, I guess Snowflake has already got something similar-ish, or time travel, I guess. Not quite.
Yeah, so Snowflake has time travel. Like some of those, like data warehouse platforms, that even the new ones, they have maybe some notion of like doing time travel, but it doesn't really satisfy like the guarantees that we like about using Git. So like being able to create a branch, work in isolation, have this kind of CI/CD notion of like merging only after a set of tests has passed. So this is something that like ideally is part of our vision. We would like to introduce to other things and not just the data lake. But like from the scars on our backs, we know how painful this is on the data lake. So we wanted to solve that first. But yeah, the idea is to, pardon the euphemism, but we want to branch out to other data sources as well. So data warehouses definitely, and maybe even other types of stores.
Oracle SQL Server, for instance, maybe, no?
Maybe someday.
Yeah, fair enough. So I just had you a look at your quick start, and you've got a Docker Compose there. It's got a Postgres with a container in front of it. I'm a serverless guy. I like to offload things. So I'm opening things up for your product pitch. Have you got like a managed service that we can just sort of spin up and sign up to, rather than having to manage a Postgres database or a Docker container on Fargate or something like that instead?
So that's a good question. So we don't have a managed offering yet. It's something we'll focus on later. We wanted to kind of nail the lakeFS experience first. It's something that's like we believe it's probably bound to happen at some point. What we are doing is trying to kind of smoothen the experience as much as possible for you to host lakeFS yourself. So yeah, you can spin up your own Docker containers and do all that, but we also have a Helm chart. So if you're using Kubernetes, installation takes about 5 minutes. Postgres is something that we started with. Down the road, we do have plans to eliminate it completely. So all the metadata is being stored back to the object store, and lakeFS itself remains a mostly stateless component, with the actual state being in S3 or whatever object store you're using. So we want to make the installation as easy as possible. It's kind of like, we believe this is the right thing to do. And down the road, of course, maybe at some point introduce a managed service for this.
Yeah, sounds fascinating. I mean, I think S3 recently, AWS announced for S3 recently around read after write consistency. So I think using it as a kind of in some sort of database form makes a lot of sense these days. So that's going to be fascinating, and yeah, having less things to manage is probably a good idea, even though I know a lot of us are data engineers and managing Postgres clusters should be second nature to us. But hey, you know, everyone's
it's not trivial,
isn't it?
Yeah.
Well, that's been a fascinating talk, Oz. You definitely given me some inspiration to spin up a lakeFS implementation. I don't have an EKS cluster lying around at the moment, or a Kubernetes cluster on another cloud, but I might just spin up your Docker Compose or run it with Fargate and perhaps Postgres Aurora or something like that. But
I think running it locally, like doing that Docker Compose, it's a one-liner. You paste it in, you get a running lakeFS instance that you can play around with. You can point your like local Spark installation at it and start like experimenting with it. And you can actually map your actual production data into that lakeFS installation so that it looks like you're working on like your actual lakeFS, your actual data lake. And it's all running locally, and you can start experimenting with it. So that's pretty cool.
Fascinating. Like I said, looking forward to having a bit of a play around with it. And thanks once again for your cool talk. And perhaps we'll get you to come back, in say 6 months' time for a follow-up talk. Hopefully, managed service by then, just for lazy folks like me. But yes, thanks once again. All right, we'll be back again next month. That's it for the data engineering meetup this month. So thanks so much. And thanks to our awesome speaker, Oz Katz from Treeverse. joining us all the way from Tel Aviv. Thank